Good afternoon to everybody here in the audience and on the web, and above all to our distinguished speaker, Professor Barish, Nobel laureate in physics in 2017 for the discovery of the gravitational waves, who is connected with us, I think, from his home in Pasadena, California. And good afternoon to Professor Eugenio Coccia, who is here in person and who will help us in interacting with Barish. They are long-time close friends, and they collaborated in the field of gravitational waves. Eugenio Coccia is the first rector of the School of Advanced Studies, GGSI, which means Gran Sasso Science Institute, established in 2016 in L'Aquila after the disastrous earthquake. It is an international school on the model of Sissa in Trieste and Normale in Pisa. Barish is a frequent visitor in Italy. Last year, he attended the inauguration of the academic year of the Gran Sasso Science Institute, along with another Nobel laureate, Carlo Rubbia, whom we know very well here in Trieste. And last January, I like to remember this, just last January, just before the spread of the pandemic, Barish was in Trieste for a colloquium at SIS. I remember that just that day was his anniversary, and we celebrated it with him and with his wife, with a dinner and a cake with candles, together with a group of physicists from SIS and the director, Stefano Ruffo. Eugenio, since you are a long-time friend of Barry, perhaps you would like to add something more before I introduce Professor Barish.
Well, yes, thank you, Fabio. I would like, first of all, to say hello to Barry, and also I would like to mention that he is a member of the scientific committee of the Gran Sasso Science Institute, so we need another link we have between us. Also, I would like to share with him the joy for the recent discovery published just yesterday in Physical Review Letters about the discovery of a merger of two black holes into 142 solar masses black holes, which is a black hole in a range of mass which was never detected before, gravitational waves or electromagnetic telescopes. So I think that's a very recent discovery we would like to mention, which I'm sure Barry is happy about.
Thank you, Eugenio. And I would start with a statement which I found on the web, a statement from Barish. This one. We scientists, said Barish, especially we physicists, are presumptuous and think we can do everything better than everybody else. But one thing I realized early: I have some talent in managing and organizing things and people. Well, in this statement is hidden, in a certain way, the secret of the success of Barish, and the reason for which he was awarded the Nobel Prize in Physics with his colleagues Rainer Weiss and Kip Thorne for their contributions to the LIGO detectors and the discovery of the gravitational waves caused by cosmic cataclysms. The detection of the gravitational waves is certainly one of the greatest discoveries in physics in the last 100 years. They were theoretically predicted by Poincaré in 1905, but it was Albert Einstein who, in 1918, imagined these waves as perturbations of the space-time in the framework of the general relativity. These waves remained a sort of dream until the 14th of September 2015, exactly 5 years ago, When the two interferometers of the LIGO collaboration, one in the state of Washington at the Pacific coast of the United States and the other one in Louisiana and the Gulf of Mexico, registered for the first time the signal of gravitational wave emitted by the coalitions of two black holes in the following years. And in the following years, many other events involving black holes and neutron stars were detected by the two American interferometers and by the European interferometer Virgo in Italy, in Tuscany. And when in 2017 the detection of gravitational waves was linked to the optical observation of the source of a gamma ray burst originated by the merging of the two neutron stars, this marked the very beginning of the so-called multi-messenger astrophysics, a completely new field of research of the universe. About 1,000 physicists and engineers work together in this international collaboration between LIGO and Virgo in Europe, in USA and the other continents to definitely not an easy task to manage this very ambitious enterprise. And Barry Barish played a key role in the reorganization of the LIGO group and in the technological and scientific collaboration between LIGO and Virgo in USA and in Europe, in Italy, with the help of his Italian friend and colleague Adalberto Giazzotto, who unfortunately passed away just after the detection of the first gravitational waves. Well, this is the scientific side of our speaker, who is now Professor Emeritus at the California Institute of Technology. But for EASE of 2020, he preferred not to talk explicitly about gravitational waves, but he preferred to reflect about the meaning of the man's desire for knowledge, about the curiosity-driven process through which we ask ourselves why, what, how. Professor Barry Barish. Hello, Barry. Nice to see you again in Trieste, virtually this time, unfortunately not in person. Anyway, it's a very wonderful occasion to have you again here in this, on this occasion. You prepared a sort of a reflection, about sort of rethinking about the curiosity-driven processes of science. Okay, is it right?
Thank you. And it's great to be back in Trieste, even if it's from California. I had a wonderful visit in January, and a wonderful 6 months until the pandemic came in Rome. Today, I'm going to actually talk about fundamental research, the kind of research that I've done, that we just heard about, but really the human part of the problem. And in particular, what I call, and what's called inquiry-based research, driven by curiosity. So it's curiosity research. We have very forefront research that's very directed. Probably the biggest problem right now is how to develop a vaccine for the COVID-19. That's a very directed and very high-level research. We also have research that I would call observational. A good example is telescopes that are made with looking in a different way and just observing the sky. I'm going to focus today on the kind of research that's driven by just human curiosity, how that comes about, and what are some of the issues involved in actually the human quality of doing this kind of research. First, I'll just show a slide from 2 days ago. As Eugenio mentioned, we made a discovery. It's an illustration. This discovery, this is the picture. I'm not going to explain it in detail. It's the signal seen in the west coast of the US in Hanford, Washington, signal seen essentially simultaneously in Louisiana in the middle, and in near Pisa, Italy on the right, 3 different places in the world, and then reconstructed to come from very massive, what we call black holes, colliding together. But we never believed and still don't understand how there can be such heavy, what we call stellar black holes. So this is an illustration for me of us observing nature, not driven by an exact goal that we were looking for 80, 85 solar mass black holes or something, but we made a discovery announced and around the world, distributed 2 days ago, based on us looking even where we don't necessarily expect to see something. And that is kind of the genesis of curiosity-driven or inquiry-based research. So let me go on. Let me talk about myself just a minute and how my attitude came about. And if you look at the little picture on the right, it's a glass of water with an ice cube sitting in it. And like all children, I asked a lot of questions when I was young. And basically, as a kid, that's how we learn about the world. And like all other children, the primary people I asked were my parents. So I would ask my father a lot of questions. And the first one that I recall that where he didn't answer me, couldn't answer me, was the question of why ice cubes float in water, since they're made out of water. It's a curiosity question, totally. And he didn't know the answer to it. He's not a scientist, wasn't a scientist. And that was maybe the first time I was a scientist, because I was curious about it. I went elsewhere to the library and so forth, and basically found out the answers. Of course, wasn't the first one to find out the answers, but the fact that ice, when it is frozen, expands just a little bit, makes it lighter in terms of a given space. And so it's a little bit lighter and floats on the top of water. And that's the first maybe introduction to curiosity-driven research. It's important that I reflect on the fact that as a child, I wasn't exceptional. All children ask and ask and ask lots of questions. That's how we advance in the world. Unfortunately, we don't do very well at stimulating that as kids grow up. So in the little cartoon at the right, you can see that the teacher, if she finishes her first year, is a success if she hasn't destroyed the kids' ability to ask questions. And that's our biggest problem in school. As young kids, we ask lots and lots of questions at the age of 5, 6, 7, 10. And by the time we're grown up, and we teach in university even, that question asking has died away for most of us. Some of us still have it and maybe do research, but one of the biggest failings, I believe, in teaching is that we don't stimulate curiosity. Instead, we basically kill it. And here's several comments just relayed to it. First, Carl Sagan, famous for Cosmos, the big popular television series that explained nature to a very broad audience. And he said, every kid starts out as a natural-born scientist, and then we beat it out of them. A few trickle through the system with their wonder and enthusiasm for science intact. And so he's saying the same thing, that somehow, despite the fact that we teach a lot of things, we somehow beat this natural questioning, ability to work through problems out of our young children, and we would do much better if we didn't. The second one is by Leo Zellard, and he was the person, a very good physicist, who was responsible for convincing Einstein to write the letter to President Roosevelt to start the Manhattan Project, where the atomic bomb was made. And he says, as far as I can see, I basically remained as a scientist because I didn't grow up. that part of the slide's covered up for me by the way that it's shown on my screen, so I can't see it. The third one I'll show you is just a little cartoon, which to me illustrates again the problem. Here's two little dogs. They're looking down at a dead cat. And one says to the other, "What happened to him?" And the second one says, "I don't know. He just came up and started asking a bunch of questions." And on the bottom is a very common statement that really has to do with curiosity in the cat. Curiosity killed the cat is a very common comment, which is exactly the opposite of what we want and believe, that curiosity kills the cat instead of curiosity stimulates us to learn and to even eventually some of us be researchers. A second similar kind of cartoon that I found shows a bunch of dead cats in a research in a room, and the police that come in and see the dead cats say, "Notice all the computations, theoretical scribblings and lab equipment." Norm, yes, curiosity killed these cats. So we have in our society a well-known statement that basically is the opposite of what we want and need to become really curious and practicing adults and scientists. It reflects not just whether we become scientists, but just the society itself. It's a crime, I think, that we live in a modern society where most of the population holds a cell phone in their hand and has no idea what it is, how it works, how it tells them where they are on the earth, or how they manage to send signals and voices to each other. We have television sets, which probably most people have no idea how it manages to get and transmit and show us a picture for us. We fly in airplanes, and most people don't understand how an airplane and why it flies or how it flies. Or we use a microwave oven, for example, in the kitchen, and how many people that use a microwave really understand what's happening and how it manages to cook the food. So it isn't just being a research scientist, but by killing our curiosity, we basically kill a lot of the richness in being a modern human being. Back to science. Maybe the first well-known curiosity-driven discovery that I should reflect on is Galileo. So Galileo in 1600s, early 1600s, for the first time took lenses at that stage that had been developed for eyeglasses and was able to make a telescope. He didn't invent the telescope, but make a telescope that was powerful. And he was curious enough to point it and look at Jupiter. And when he looked at Jupiter, he discovered that Jupiter had 4 moons. And that was the beginning of modern astronomy. And it was basically curiosity-driven research in the purest level. He developed an instrument that was good enough to do something, had the curiosity of looking and trying to understand something in space, Jupiter, and made a fantastic discovery. In modern life, of course, a lot of discoveries are made that way in the field, my field, or field near me. In the big laboratory in Geneva, Switzerland, in CERN, the big question that they addressed is, how does this equation of Einstein, E equals mc squared, work? If you start with energy, how does it really create mass? It's a fundamental question that we hadn't answered in 100 years since Einstein. And although the idea of how it might happen, or an idea, had existed for 50 or 60 years, it took this large, ambitious, curiosity-driven research at the largest scale at the CERN laboratory to develop 2 sophisticated instruments that for the first time were able to discover the mechanism which had been proposed 60 years earlier, but until you see it, you don't know, responsible for creating mass in nature. A second one, again close to me, is the understanding, started from the understanding of how our sun burns. How does the sun heat us? Where does the energy come from? And how does it work? The idea was that the process of nuclear fusion is burning the elements deep in the core of the sun. This was an idea, again, that was around for some time. And in order to test that idea, a product of that is a little particle called the neutrino. And the experiments were made to detect this neutrino. They found the neutrino, and that showed that neutrinos came from the sun. But when they found it, they found the wrong number of neutrinos, actually about 1/3 of the number of neutrinos that one would calculate from the heat and power that's emitted from the sun. That was a big puzzle for tens of years, and it took a second discovery to understand that, and that is this little particle that they were detecting. The neutrino itself had a feature that we didn't know at the time, and that is there's more than one kind of neutrino, and in the path from the sun to the earth, they change identity. And so the ones that were looked for, that when they were emitted from the sun, some had changed to another identity by the time they had gotten to the earth. This is commonly called neutrino oscillations. Lastly, there's of course our experiment looking for gravitational waves. The idea that there are waves in nature in gravity, just like there are in electricity and magnetism. In fact, Einstein's first idea that there were gravitational waves came from, again, just the idea that they must be there by, again, just logic, if they are in electricity and magnetism, because there's similarities in the equations that describe the two. So he proposed, without deriving it from fundamental principles, that gravitational waves exist, and we detected them 100 years later. That's all based on what I call curiosity-driven research, and forming questions that are very specific, inquiry-based research itself, and often in modern days requires large-scale projects, which are like the one that was described at the beginning that I've worked on. The modern technology, and so we can do experiments and research now that couldn't have been done a decade ago, so you don't have to worry that somebody did it before you. And often big risks, because we don't know whether they're going to lead to anything interesting or not anything interesting. And there's often a lot of resources that are used. So the whole game is one that's driven by our curiosity, takes resources, takes imagination, and takes the drive that human beings have to understand nature. Sometimes it leads to practical applications. Here's an example. Out of absolutely fundamental research, there was a principle called stimulated emission, again by Einstein. And that principle was looked for in physics labs in about 1960 and discovered with no idea that it was of any use. It turns out to have a focusing property in that the photons that are created, or the beam of light that's created, is very focused. It was realized a decade or so later that that could be used as a focused beam of light, and that became the origin of the laser, a $20 billion industry in the present world. And of course, we use lasers for everything from pointing to a screen in a talk like this, if I actually were in Trieste, to doing sophisticated operations on our eyes or any other many other applications. A second practical application of an absolutely fundamental curiosity-driven research is the discovery of what was called nuclear magnetic resonance. Nuclear magnetic resonance is a property of nuclear physics. And that property can be used, and has been used, again discovered sometime later, as a way to image the body. It's changed its name. People don't like the word nuclear when you work with humans. And so it's called magnetic resonance imaging, which is the best imaging device we have of the human being now, which came about not by directed research, but by basically understanding a basic principle of nuclear physics that was understood in laboratories in the world in the last 50 years. Maybe the most important discoveries often are even less directed. They come about out of just the fact that you're able to observe something that maybe you didn't expect. A little example of that, maybe not so little, is the one I gave at the very beginning, that in the discovery that we just made of black holes. Maybe they're not black holes, but black holes that are very, very heavy, that they weren't expected in nature, but we looked anyway, or were able to look. The most famous, I think, or most important example of this kind of discovery, which you might call serendipitous discoveries because they're made without really knowing they can be made, was the discovery by Fleming in 1928. He was studying Staphylococcus, a bacterium that's responsible for blood poisoning, and he took a vacation. And when he came back from vacation, he found that there was mold on his mold on his cultures, on his devices. And he, instead of cleaning it, which would be the natural thing to do, had the curiosity to realize that these molds were somehow killing his Staphylococcus, and he was having trouble doing his experiment. So he became curious, and in the end understood by studying the mold that the basis of the mold could kill bacteria, and it was the beginning of understanding penicillin, which is perhaps arguably the most important health discovery to help our health in the 20th century, which came about by a curiosity-driven, serendipitous discovery by Fleming. And he said, one time, again, my slide's a little bit covered up. One sometimes finds what you're looking for when you do research, but when he woke up on September 28th, he certainly didn't plan to revolutionize all of medicine by finding the first of the world's bacteria killers, but I guess that's what I did. This is a picture of his mold, actually, that was put on auction in London. There's another side of this whole story, and there's a very nice book written by Roy Calm, and you can see the name of the book. The name of the book is The Ratchet of Science. A ratchet is a tool that we use that always goes forward, never goes backwards. As you move it, it keeps moving forward and forward and forward. And research is that way in his mind. As we learn something, you can't unlearn it. So we learn like a ratchet and it moves us forward. But in his story, his concern is really what I started at the beginning, that curiosity kills the cat. And that is that we can learn by our research important new things, but not have the maturity, the sophistication, the culture, the governments that are able to handle it. Probably the best example in the last decades, of course, is the discovery of thermonuclear devices, but the use of them as weapons. So in the end, doing the kind of research that I'm talking about can be used for basic science. It can be used for applied science. How do we use something? I gave examples of both. And in the end, I think it is really a very romantic and wonderful way to do science, but affects humanity in a very important way. And we could do better if we stimulate curiosity. So curiosity, I believe, is a very special human quality. It's something that we need to nurture and use and enjoy because it is so valuable to have. And that is saying something about something that should be improved, I believe, in our education system. We should be curious, we should stimulate it. But as said in the book that I described, we must always take responsibility for the outcomes. Thank you.
Thank you, Barry Barish, for your thoughts about the curiosity-driven science. Just one thing. Not only humans have curiosity, also many animals, many which we share our lives on the earth, have the same instinct of be curious, to find the new things and to explore new environments. This is sort of something which is in the genes of many living beings, not only humans, I think. For instance, the cats, for instance, is the most outstanding example of curiosity in animals, for instance. Do you think so?
Yes, I agree with you. I think maybe humans are more extreme.
Sure.
I really pick on humans because, well, maybe we do it with animals too. We should stimulate this wonderful quality rather than kill it. And if we do, there's consequences, of course. That's why we have sayings like curiosity kills the cat. But we try to train our animals so they don't do crazy things. In a sense, when we train ourselves or teach in schools, somehow curiosity is a wonderful quality that we should enhance and not kill.
Sure. Eugenio, what do you think about this process of curiosity in science, in your experience, for instance?
Yeah, I think that.
I think that that in a sense it's very nice for us maybe to understand this. It's very hard to, and as science becomes harder, takes major resources, you can't always succeed. I spent 10 years at the Gran Sasso laboratory near Eugenio, looking for something called magnetic monopoles, whether magnets have single poles, like a North Pole and a South Pole. We didn't succeed. We never saw one. That doesn't make the research not worthwhile, but it's hard to convince people who fund research or the society to support research that's really driven by our curiosity, unless everybody appreciates curiosity well. So I think the research in my country, in the US, is far too conservative. The peer review system itself, which we use to select what research is done, tends to be very conservative, because if somebody proposes to do something that you don't expect, and you're asked to review it, you tend to be conservative about whether they should do it. So in general, I think research would move much faster, we'd make more discoveries if we could be more adventurous and more curiosity driven.
Okay, Eugenio, do you want to add something, other considerations about the curiosity driven in science in your personal experience too?
Well, of course, let me thank Barry Barish for this very, very nice, wonderful talk about curiosity. I think that why we are naturally curious is also because we are particularly attracted by truth and beauty. And let me report just in a few minutes, just going at the root, why it is important to study basic science or to be, let's say, attracted by what we think is maybe important to know. And this is a very famous example, which I can do, is that when in 1969 Bob Wilson was called to justify a multi-million-dollar machine for the Fermi Lab to the Congressional Joint Committee on Atomic Energy. And backing the trend of the day, Wilson emphasized that it had nothing to do at all with national security. This was the question. Why we want to spend such amount of money for a curiosity-driven enterprise? What will be the output for national security? And he responded, that if I may mention, the response is wonderful, I think. He said, it only has to do with the respect with which we regard one another, the dignity of man, our love of culture. It has to do with are we good painters, good sculptors, great poets? I mean, all the things that you really venerate and honor in our country and are patriotic about. In that sense, this new knowledge has all to do with honor and country, but it has nothing to do directly with defending our country, except to help make it worth defending. I think these are wonderful words.
It's a strong statement, but very powerful, I think. What do you think, Barry Barish, about this statement?
Yes, I remember when Bob Wilson made this statement, and I think I reacted to it very much like Eugenio and you. It's a very, very powerful statement.
Eugenio?
Yeah, I mean, it has to do with the questions like what is the usefulness of a sculpture of Michelangelo or of a symphony of Beethoven? I mean, and science is on the same track.
Mm-hmm.
Yeah, well, I mean, I emphasize the things that we can see and do with science, but it has the aspect that you're emphasizing, that it's basically naturally beautiful. It enhances mankind, and that's as much a reason to do it as we play music or art. We also have the fact that we learn more about nature.
Sure.
Okay, I think now time is over. I thank very, very much Barry Barish. And Barry, we hope to see you again in Trieste in person this time, next time, not virtually. And I thank also Eugenio Koch from the GGSI in L'Aquila for sharing this time together, talking about the curiosity-driven process in the humans and not only in humans. Thank you to everybody. Bye-bye.
Thank you.
Thank you.